So higher order linear systems, we're not going to do a huge amount of calculations here. What we're going to do mostly is look at some pictures and think about how we can put together the stuff we know about two-dimensional systems to think about three-dimensional systems. So if we have n equations and n variables, we can write it as y prime of t equals my, where m is an n by n matrix. So here's a system of equations. Can we turn this into a matrix form? Sure, we'll set capital Y of t as a vector, consists of the three components x of t, y of t, z of t, and then y prime of t is dx dt, right? It's the velocity components in three dimensions. So if we look at this system of equations, our left-hand side is y prime of t. That's our derivative. The matrix of coefficients is -2, -4, 2, -2, 1, 2, 4, 2, 5. And then we multiply it by our matrix y of t. So we get a 3 by 3 matrix. The theory works exactly the same as it does in two dimensions, right? How do you find the solution to this? You find the eigenvalues and the eigenvectors, and then you put together the solutions depending on what kind of eigenvalues and eigenvectors you get. So how do we find the eigenvalues and the eigenvectors? Well, it's the same kind of thing that you would do in two dimensions, except now it's in three dimensions. So you'd set up -2 minus lambda, -2, 4, and then 1 minus lambda. I always write the lambda terms first because then that helps me figure out my spacing. And then 5 minus lambda down here, 2, 2. So we set that equal to 0. So what's that? Well, if you remember when we were looking at three-dimensional 3 by 3 determinants, we set up our checkerboard, and we pick a row or a column to expand around. Here, there's no zeros anywhere, so we'll just go along the first row here. So we'll take -2 minus lambda with a positive sign times the determinant of the matrix you get by looking at what's left after you get rid of the row in the column that the -2 minus lambda is. So that's 1 minus lambda, 5 minus lambda, 2, 2. That's these four terms. And then we get minus from the checkerboard, -4 times the determinant of the matrix that you get when you get rid of this row that the -4 in and the column is. So that's -2 and 4, and 2 and 5 minus lambda. And then you get plus from the checkerboard, 2 from the row, and determinant of -2, 4, 1 minus lambda, 2. And we're not going to calculate that out, except we want to point out here in this term, you get -2 minus lambda times the quantity 1 minus lambda times 5 minus lambda -4. And when you distribute this, you'll end up with a lambda cubed term. So a 3 by 3 equation to find the eigenvalues, you get a lambda cubed term, a polynomial of power 3. You have to solve that. Factoring doesn't work. Usually you have to do some kind of, factoring often doesn't work. You have to do some kind of numerical analysis. So the characteristic equation in general will be of degree n, and then you have to find all the roots, usually by numerical means. So here's an example. In example 1, if you grind through finding the eigenvalues and eigenvectors, you get this. You get 3 distinct eigenvalues, and each one's got an eigenvector. What's the solution? Well, we just sort of extend the same kind of systems that we had back in for 2 dimensions. Y of t will be k1 e to the 3t, that's lambda 1, times v1, 2 minus 3, 1, plus k2 e to the minus 5t, 2 minus 1, 1, plus k3 e to the 6t, 1, 6, 16. So the same kind of thing we did before, except now we have 3 terms instead of 2 terms. And so there's our solution. And the problem is can you actually sketch this in 3 dimensions? And here's a picture of 3 dimensions. We'll, don't know what that did, but we'll zoom out a little bit. There we go. So which of our 3 vectors is our eigenvectors? So 2 minus 3, 1, that's this one. So v1 is here. We'll do that here. So this is v1. v2 is 2 minus 1, 1. So that's this one. Now I figure out where to put my label. v2 is that one. And then this one is v3. And you can tell v3 because it's got the biggest number in it, 16. So what do we know about this? Well, we know that v1 has got a positive eigenvalue. v3 also has a positive eigenvalue. So we have a solution, an eigensolution that goes out in that direction. 0 is an equilibrium. And then we have another solution going out underneath the plane in that direction. v3 is also positive, so we have positive eigenvalues. So we have that going out, and then another one going out in the other direction. v2 is a negative eigenvalue, so in fact here we're actually going in, and then that's going in. So that tells us what's going on with the eigenvalues and the eigenvectors, right? But what's going on for the rest of the plane? And that's a little bit trickier to look at. What we can do is we can say, well, v1 and v3 are both positive eigenvalues. So in the plane that is spanned by v3 and v1, what we're really having is a source, right? Lambda equals 3, lambda 1 equals 3, lambda 3 equals 6. And then we have a third dimension along v2 where lambda 2 is minus 5. That's where we're actually going towards 0. So here, this blue plane, that didn't work. So in this blue plane, that's the plane spanned by v1 and v3, right? And v3 is this one, and v1 is that one. And v3 is the stronger of the 2 eigenvectors because it's got an eigenvalue of 6. So in this plane, in this blue plane, what is my solution curves looking like? Well, they're coming out tangent to v1 and going up parallel to v3. Right? And so we have v3 continues that way, v1 continues that way. So these are lying in this blue plane, which is a little bit hard to draw. This orange line, right? This is vectors, that's v3, v2, and that's going in. So this is v2, v2, lambda 2 is less than 0, so going in there. So what we've got is a plane which looks like a source if we just look at the plane, and then we have a line that looks like everything's going in. So if we pick some point that's sitting out in space here, you can break it down into a part on the plane, right? So this point can be thought of as a point lying in the plane, and plus a point on in the span of v2. So every solution has a part that lies in the plane plus a part that lies along the line. So what does that do? Well, for this point, right, you're going to be going in because of this, but then you'll be going out along this way. So this point, as t goes to infinity, it's going to approach the plane because this point is going in, but it's going to be going out because of that. So it will be going something like that. And in backwards time, it's going out parallel to this, but it's getting closer to this line as it goes out. So it sort of comes in along this eigendirection, and then it switches to being in the plane, and it goes out that way. So it's a little bit hard to picture, but you know, a plane with a line going through it, and you come from the line, transfer to the plane, and go out along the plane of dynamics. So here's this system and its eigenvalues, eigenvectors. What's the general solution to the system? So here we've got complex eigenvalues, and here's the two vectors that go along with it. And we have lambda 3 equals 1. That's a regular eigenvalue. So what's the solution? Well, it's the same thing that you would write down in 2 dimensions. So we have K1, complex eigenvalue means you have e to the t cosine t, because a equals 1, b equals 1, times the vector -5, -1, 1, plus K2 e to the t times the vector 1, 1, 0, plus K3 e to the t times the vector 3, 0, -1. These two together, that gives me a spiral source in the plane that's spanned by V1 and V2. And then this is just a source in the plane line spanned by 3, 0, -1. So if we go to a picture, right, again, the plane here, this is spanned by V1 and V2. Span of V1 and V2, and this is span of V3, right? So there's V3 going out along that. And V1 and V2 is this plane. And what we have is a spiral source. So in the blue plane, we have spirals going out like that and spiraling in towards the origin. So we have 2 components, right? We've got a plane in which we're just doing a spiral source. We're just coming out in spirals. And then we have a line where we're just going away from the origin. So what's the combined effect of those if we take a point somewhere out in space that's not either on the plane or the line? Well, again, it can be broken down into 2 parts, right? This point has a component that's along the plane and a component that's along the line. So this is the component along the plane, this is along the plane, and a component along the line. This component tells me that I'm spiraling out, but I'm spiraling out sort of along this line because that's getting bigger as well. And in backwards time, I'm going to be spiraling in, but I'm going to be spiraling in around the orange line as I go back in. So the orange line is sort of a center for the spirals. They'll spiral out around that as t goes to infinity. And so 3-dimensional cases can get quite complicated depending on how you want to envision them. 4 and 5 and 6 dimensions get even worse. The solutions, however, if you want to write down the solutions, they work pretty much just the same way they did with in 2 dimensions, and that happens because every polynomial, when you factor it, is either, I mean, the roots are either complex conjugates, in which case we get various types of rotation, or you have single roots or double roots, and so you just get the same pictures put together in complicated ways.